Hi, this is Professor Fernandez. We are working on class notes A in lesson 18. In this example, we are going to go back to the system that we talked about in the previous lesson. And in the last video, we saw that using the website that I mentioned then, the phase portrait for the system consists of all these concentric circles, and they're traced out counterclockwise. So in this example, we are going to actually be able to mathematically prove that this is indeed the phase portrait, the set of all concentric circles of varying radii centered at 0, 0, the origin, and trace counterclockwise. So how do we do that? Well, we are actually going to find the orbits to the system and show that they're circles. So that's actually part B here. And then, what I've given away, what the description of the phase portrait is, that's that concentric circles all centered at the origin description. But anyway, let's start with part A here. So how are we going to achieve this? We're going to show that the general solution is this first, and then we'll get on to part B, and part C. So how do we show that the general solution is what is written up here? Well, so this is a system that starts with x dot and says that that's equal to negative y, and then tells you that y dot is equal to x. So you might have already seen how we can connect these two equations. If I start with this one and I differentiate it with respect to t, then that means on the right-hand side I'm going to have minus y dot. And then I can use this second equation in here. So that gives me minus x. All right, so this is x double dot minus x equals 0, which is, x double dot equals negative x. And then I can bring over that negative x to give me x double dot plus x equals 0. This looks like an equation that we have solved before. I'm just gonna put it in quotes here. This is the equation y double prime plus y equals 0. I put it in quotes because I don't want to confuse you and tell you that x, or suggest that x equals y. That's not true. We are told here actually that x is y dot, so we got to be careful with our letters and notation here. But the point is that you might not recognize this as something that we've solved in the course before, but we have. It's just in a different form. It just looks different, but actually we've solved it before. So all of that is to say that this is a constant coefficient second order linear differential equation, and it's homogeneous. So we know how to solve this. So we write down the characteristic equation, that's r squared plus 1 equals 0. And then we solve here for the r values, so we get plus or minus I. So this is all going back to content we learned in the second unit of the course. And then if you remember that far, the fundamentals far back, the fundamental solutions are e to the alpha t cosine beta t, where alpha and beta are the real and imaginary parts of the r values. In this case, we have no real parts, so the first fundamental solution is just cosine of beta t. Beta is the imaginary part, and imaginary part here is 1. So just cosine of t. And x2 of t, which I'm calling the second fundamental solution for this ODE, x2 of t, is sine of beta t, so that's sine t. So the general solution, x of t, based on all our theory from Unit 2, is the linear combination of these two fundamental solutions. So that explains, I'll scroll up here, this x of t formula. So we've derived that. So how do we get the y of t formula? Well, this is where we go back to the system, and we kind of have to figure out what it's telling us. So the system is telling us that x dot equals negative y. So if I go down here, if x dot is negative y, then y is minus x dot. And I know x, so I'm just going to differentiate this function. Okay, so the derivative of cosine is negative sine, and then the derivative of sine is cosine. And then I multiply this minus 1 in, and I get c1 sine t minus c2 cosine t. And that is my y of t function down here. So I'm going to scroll up and show you that that's what's over here. Okay, so we have finished part A, and we've now derived the solutions, the actual solutions to this system. One of the reasons I wanted to start with this example, and I've been kind of coming back to it, for 2 lessons now, is that it is one of the generally rare examples where we can actually solve the system, the plane autonomous system, for the explicit solutions. And I also wanted to connect it back to content that we had done earlier in the course. So now that we've solved it, how do we get the orbits? Well, remember that the orbits are the x of t, y of t curves. So orbits are x of t, y of t curves. All right, so in practice, what this means is that you're trying to find a curve in the xy plane. So most of us are used to doing that by finding a relationship with the form y equals f of x, like y equals x squared. This could be the orbit of some system. But you may think a bit more generally than that, not necessarily y equals f of x, but some function of x and y equals some number. Okay, so an example is like the one we're about to see, x squared plus y squared equals 1, let's say. So that's the equation of a unit circle in the plane. So the point is that, for a condensed understanding of the orbits, what you're looking for, if you have the solutions of the system, which have t's in them, x of t, y of t, and there's a bunch of t's, what you're looking for is to eliminate the t's, to have a relationship between just x and y, and that will give you the equation of the orbits. So how you eliminate t varies a lot if you've gotten this far of solving the system in terms of t. So how you eliminate t varies a lot by the system. For this system, there are lots of sines and cosines, and the very first identity that comes to mind for sine and cosine is this one. Sine squared plus cosine squared is 1, which involves squaring. So that's one of the reasons I'm going to start here with x, and I am going to square it, and then do the same thing with y, and then I'm going to add the results. Okay. So x squared is c1 cosine of t plus c2 sine of t squared, and then y squared is c1 sine t minus c2 sine t. Oops, that would be different from what's above. So minus c2 cosine t squared. And then what happens here? So I get c1 squared cosine squared plus 2 c1 c2 cosine t sine t plus c2 squared sine squared t. All right, and then for this one down here, I get c1 squared sine squared t minus 2c1 c2 cosine t sine t, and then plus c2 cosine squared t. And then I'm adding all of this. So first thing I want to point out is that this term plus 2c1 c2 cosine t sine t cancels with this term. So that goes away. And then what's left? If I factor out a c1 squared out of these two terms, then you can see this identity where it's going to come in a minute. And then over here, if I factor out a c2 out of c2 squared, that should have been a squared right there. If I factor out a c2 squared out of this term, then I get sine squared t plus cosine squared t. So once again, using so this on the left-hand side is x of t squared plus y of t squared. And then using my identity, sine squared plus cosine squared is 1. Then I can use that here and here to leave me with c1 squared plus c2 squared. And at this point on the left-hand side, I'm going to drop the of t here, the reminder that x and y depend on t. We know that because we found that dependency explicitly. But for the purposes of the direction of the orbits, we don't need that information anymore. In fact, for the orbits, we would kind of prefer not to have that information. It's useful to know if you can figure out, the t value that you're at when you're tracing out the orbits, but it's not required. So this is the equation of a circle with center 0, 0, and radius square root of c1 squared plus c2 squared. So if I were to then go off and try to draw the phase portrait, I would draw the XY plane, the phase plane. And then what am I going to draw? I'm just going to draw circles, all with center 0, 0, so they're concentric, same center, and different radii. So I'm just going to draw a bunch of circles that have that form. There we go. This is my rough drawing of circles. And then they all have different radii. So that's why some of them are small, some of them are big. One thing we haven't done yet is to put in the direction, and we will do that in a future video. But let me just go over to the website that we've been using and show you that indeed this is the face portrait. And you saw this in the previous video as well, so I kind of just left that up. But I'm going to clear the curves here and again put this in Runge-Kutta 4 to get a more accurate numerical solver. So you can see here the direction field, and I'm just going to tap on points on the screen, and the applet is going to numerically solve for what the points on this curve are. So if I keep tapping a bunch of points, then indeed, you can see that this website is confirming what we just showed mathematically. The thing is that I've tapped maybe 6 or 7 points on the screen. You might worry or wonder, how do I know that all of the orbits of this system are circles, right? I only have plotted a very small portion of the phase plane for this system, and that's really my advertisement, if you will, for learning how to do this mathematically and not relying solely on the calculator or the computer algebra system or a website. Because what we've done here is proven that all of the orbits are concentric circles with this particular radius. So we don't need a computer to help us confirm that, right? On the other hand, it's the other way around. The computer needs us to make sure to confirm what the math is saying. One last thing that I'll mention here, notice that the radius, square root of c1 squared plus c2 squared, involves c1 and c2. And remember that c1 and c2 have always been, for us, tied to the initial conditions. So I'll just make a quick little connection there for you. There's no initial condition here, right? None was given. But suppose I picked, as I've done in the previous videos, let's say I'm looking at the point 1, 0. All right, so the point 1, 0 is x equals 1, y equals 0. Let's say that this is, the point that you want to start at. Then how could I set up the t-value there to figure out what t-value I'm starting at? Well, this would kind of throw us into a linear algebra problem, right? We would want to figure out what the t-value is for x to be 1 and what the t-value is for y to be 0. And then from here, we would get this system for unknowns C1 and C2. And it turns out that this system has a unique solution for any value here, A and B. So if you tell me the initial point on the plane that you want to be at, I can tell you what the t-value is for, I can solve for the C1 and C2 value there in terms of this AB and this T. Okay, so that's one interesting thing to note. In a slightly different direction, if I were to tell you the t-value, if I said, oh, at t equals 0, I want this to be at the point 1, 0, then that's more information, right? So there we can really solve for C1, C2 numerically, as numbers without having a t-value in them. How would I do that? So I would go here and I would say, oh, x of 0 equals sine of 0 is 0, so that's gone, equals C1. Y of 0 equals, well, sine of 0 is 0, so y of 0 is minus C2. So if you give me any value for x of 0 that looks like a comma b, then C1 would be a and C2 would be negative b. So what does that mean? That means that if you tell me initially where you want to start, by initially I mean t equals 0, and by where I mean the point a comma b, then I will tell you, we know that C1 is a and C2 is negative b. So I can then scroll back down and I can look at this radius, and this will be the square root of a squared plus b squared. So this will be the radius of my orbit. So again, this comes directly then from the initial vector being the vector a, b. Same thing as saying you are initially at the point a, b. So that, again, tells you a little bit about what we've expected up until now using this notation of C1 and C2, that indeed these are related to the initial conditions in the differential equation, or in this case, the system of differential equations.